Just start. So, hello everyone, and welcome to the second seminar of online seminar of the SGEB. This is the first time that we have one of our Master Prize winners presenting their work. So that's part of an effort that we try to make. I mean, as you know, we give out the Master Prizes at both EPFL and ETH set. And in the committee, we were thinking it would be nice to also disseminate the knowledge and the findings of these theses a little bit, because obviously the people get their prizes because they did a work that's highly relevant to SGEB members. So we're very happy that Nathan Kempter, who won the SGEB prize at EPFL in 22, has accepted our invitation to present his work. So he graduated from EPFL in 22 and is since then working for Alberti Ingenieur in Lausanne. And we're happy to have him present his highly decorated thesis, because he did not only win the SGEB prize for this, but also a number of other prizes. So the UPIAV prize for the best masters in civil engineering, and the SEA prize for the best masters in INAC, and the ASE Swiss prize, and the Prix Sarada et Raju Binakota. I'm not sure I forgot any other prizes, you can name them, but so yeah, we're happy to have you presenting, and the floor is yours.
So thank you. So hello, today I'm going to present you my master thesis project I did last year, so in 2021, 2022. And this project, it treats the nonlinear and seismic risk assessment of composite steel moment resisting frame. So I will be presenting in English, but at the end of the presentation, we could, for example, have a small discussion in French if you want. So here is the outline of my presentation. I will first give you a small introduction. I will then explain you the actual state of the art concerning the seismic resistance of headed shifted connectors. After that, I will show you some experimental results in order to put the actual state of the art into perspective. And thereafter, I will explain you a way to model composite structures and validate the methodology. I will then use this methodology to analyze the seismic behavior of headed shifted connectors in a real composite steel moment resisting frame building. And finally, I will discuss the actual state of the art concerning headed shifted resistance determination. So let's start. According to standards, headed shifted resistance differs between the gravity loading and the seismic loading. And with this master thesis project, we want to be able to better understand the seismic behavior of headed shifted connectors. So the main motivation of this work is, in fact, to judge the accuracy of standards treating this subject. So in order to achieve this objective, I structured my work in 6 different key parts. The first one is a review of the standard requirements. I try to look at some actual standards to know what they say about headed shifted connectors and what are also their differences. So I analyze specifications from 3 different standards: the European standards, the Swiss standards, and the American standards. The second step is a review of literature. I summarized past work with an historical perspective to better understand the subject and also his evolution. Then the third part is laboratory experiments, because we conducted 2 historical experiments at the laboratory. So 1 monotonic push-out test and 1 cyclic push-out test to record precise data. The fourth part is a modeling approach validation. Here, a detailed numerical modeling approach for a composite steel moment resisting frames is proposed and validated with the experimental data. So 3 different models are constructed. There is the bare subsystem, the simple composite subassembly, and the composite subsystem. Then the fifth part is the nonlinear building simulation, because the validated proposed numerical modeling approach is now used to analyze the, let's say, the real behavior of headed shifted connectors in a 6-story composite building that is subjected to earthquake ground motion. And then a conclusion, here the behavior of headed shifted connectors coming from the historical cyclic push-out test is compared to one coming from the building simulation. So the three analyzed standards, they determine shear stud strength as the minimum between two terms, so the stud term and the concrete term. And then reduction factors are imposed to account for a potential profile steel sheeting. So Eurocode and AIAC standards, they impose a supplementary 25% of reduction when we are dealing with a seismic design. But the Swiss standard, so SIA, does not say anything concerning the seismic design. And as you can see now in this table, without accounting for a potential profile steel sheeting, the three standards, they have very similar approaches for the shear stud strength determination. And the main parameters are, in fact, the cross-sectional area and ultimate strength of the stud, and also the compression strength and the modulus of elasticity of the concrete. So my literature review, it helped me to better understand how headed shear stud resistance has been determined in standards. So in fact, the actual monotonic resistance of headed shear stud connectors is mainly based on the work of Vist, Sutter, and Driscoll, and Olgard and others. And these authors, they used a very, very simple experiment called the monotonic push-out test. So what is a monotonic push-out test? That is a setup where a steel beam is connected between two concrete slabs through the shear stud connectors. And you can see the specific setup with the figure at left in this slide. So the concrete slabs lie on the floor, and a pushing unidirectional increasing force is imposed at the top of the steel beam. And with this type of experiment, the load-slip relationship of the specimen is analyzed, and the shear stud strength can then be easily determined. Other authors, as Hawkin and Mitchell, Zodelin, Boursi, and Sion and Singh, they just modified this monotonic test in order to be able now to impose the load in the push, but also in the pull direction. And you can see the setup with the figure at right on this slide. So this type of experiment is named the cyclic push-out test. And so increasing reverse slip are imposed at the beam-slab connection. So these authors, they mentioned that the shear stud strength decreases under the cyclic loading compared to the monotonic loading. And the 25% of reduction given in standards for headed shear stud strength when we are dealing with seismic design can then be justified with these types of tests. Elgisser and Lignos, they collected several cyclic push-out test data from the literature. And I just used this data to be able to compare the strength prediction of the standards with the experimental results of the conducted test. So in this qualitative graph, you can see that each point represents a specific conducted cyclic push-out test of the literature. And the points that are below the 45-degree dotted line, they represent unconservative prediction of strength. And we can first notice that this graph, it shows relatively high scatter, which means that the standards, they do not accurately predict capacities of the tested cyclic push-out specimen. And we also can see that the Eurocode and AIAC standards, they show more conservative trends compared to the SIA predictions, because SIA predictions are the blue points on the graph. And in fact, that's just a direct consequence of the 25% reduction for seismic design that takes place with Eurocode and AIAC standards and does not take place with the SIA standards. So the penalty factor of 25% is therefore justified to represent a cyclic push-out test. And we have therefore to keep in mind that the cyclic push-out test, they impose very large slip cycles until the rupture. And this is here a key aspect of this master thesis, and we will speak about that later on during this presentation. But for now, keep this aspect in mind. So as already mentioned, we conducted one monotonic and one cyclic push-out test at the laboratory. And these tests, they were conducted as they were in the literature. So I will only focus here on primary aspects. So as mentioned in the literature, the cyclic resistance was seen to be less than the monotonic resistance and you can see it with the figure at right. And in fact, degradation of the beam-slab interface occurs with a cycle. With each cycle, the concrete around the studs, it becomes more crushed, and this phenomenon, it leads to a concrete stiffness decrease. So this degradation is directly linked to the severity of the loading protocol, as I already mentioned. Then digital image correlation, so a DIC setup, was used to record concrete crack evolution during the loading. And it was impossible to associate DIC data with loading. So I will show you now an animation of the conducted cyclic push-out test. So let's start. To the left, you can see the load slip behavior during the whole duration of the test. And to the right, you can see the evolution of the cracks in one monitored concrete slab. And this animation is 200 times faster than in reality. So without going into the detail, this animation, it shows that the concrete slab becomes heavily damaged with loading cycles. So the more the slip is imposed, the more the slab is damaged. And I wanted here to show you this video to point the severity of the loading protocol in cyclic push-out tests. So as I already said, we will discuss about this aspect in detail later on with this presentation, but keep this aspect in mind for now. Okay. So I will now present you a suggested approach to model composite structures with the numerical model, numerical software OpenSeas. So I will describe and validate the methodology confronting 3 different numerical models with their respective conducted experiments. So the first model is a 2-story, 2-bay steel moment resisting frame bare subsystem, and it represents the first part of Elgister's experiment. So during this part, the structure was only made of steel beams, and there was no concrete slab, and so no composite action at this stage of the experiment. Concentrated plastic hinges, they represent nonlinearity, and they are disposed at locations where the plasticity is expected to occur. And these plastic hinges are defined as rotational springs in the model. The elements between these rotational springs are assumed to behave elastically, and rigid links are disposed vertically at the pin locations in order to be able to represent the support geometry. And finally, panel zones are modeled at the joint between the columns and the beams. So the beam springs, they follow the modified Ibarra-Medina Kravinkler, so IMK deterioration model. And the parameters of this model, they are determined according to Lignos and Kravinkler paper, where in fact empirical equations are given. Then the panel zones, they follow the Kravinkler model for panel zones, and they are modeled as parallelogram of rigid elements of the size of the interception of the beam and of the column. And 3 corners are pins, and one has a rotational spring that represent a shear distortion of the panel zone. And the force shear distortion relationship is assumed to be trilinear, as shown in the figure just given below. So the rigidity of the bare subsystem structure is determined with a simple pushover analysis, and it is defined as the force we impose to the structure to the horizontal displacement between the pins. And the model rigidity is equal to 7.05 kilonewton per millimeter, and the experimental rigidity was determined equal to 6.8 kilonewton per millimeter. And these differences, they can be explained because the model neglects shear displacement. And I can thus affirm that the model represents more or less well the reality in terms of rigidity. The cyclic protocol of the composite experiment is imposed also to the bare structure. And this protocol, it consists of 3 different loading protocols that are succinctly imposed. And these protocols are the AISE protocol, the near fault protocol, and the collapse consistent protocol. And results in terms of shear drift relationship are given beside. The second model represents Yamada and other simple composite experiments. And with this experiment, a composite beam is embedded in a rigid column, and vertical displacements are imposed at its edge. So the model, it follows the macro modeling approach described by Elgister and others with some modifications. So I will now explain you the main steps of this approach, element by element, and also its modifications I made. So the composite beam is assumed to be a steel beam with a modified inertia. And this inertia is named the equivalent inertia, and it is assumed to be equal to 50% of the composite inertia under positive bending and 50% of the composite inertia under negative bending. Then the floor slab is modeled as three axial nonlinear elements that are disposed in parallel. So the first one, it represents the mechanism of the bearing of the slab and is assumed to only work in compression, so with positive bending of the composite beam. The second one is the strut and tie mechanism, and it represents the effect of the ties coming from the transverse seismic rebars and of the two compression struts that are acting with a 45-degree angle. And this spring, it only works in compression, so with positive bending of the composite beam. And finally, the third and last spring, it represents longitudinal reinforcement and is assumed to only work in tension, so with negative bending of the composite beam. And this spring accounts for longitudinal rebars that are present in the plastic effective section of concrete under the negative bending. And all these three springs, they are assumed to follow a peak-oriented IMK behavior without a cyclic deterioration. Then the beam-slab connection is modeled with zero-length axial elements that describe shifted connectors. So the first element is disposed at the end of the floor slab strings, and it represents the effects of all the studs that are disposed in this interval. So the interval between the edge of the column and the first stud location. The other elements are disposed at real stud locations. And the resistance of the stud is determined according to Suzuki and Kimura's empirical equations, because Suzuki and Kimura, they propose ultimate resistance equations of shear studs that are different for both loading directions, so under positive and negative bending.
So maybe, I don't know, it seems I'm not the only one having trouble hearing anything.
Yes, I can't hear anything.
And not see anything here. Oh, but it seems that
Here's muted.
Nathan lost connection and is trying to reconnect. So
Okay.
let's hope he manages.
Sorry. Zoom just crashed.
Oh,
Sorry.
okay. I mean, we can hear you again.
He's connected.
Now we can see a beautiful mountain picture. Okay, perfect. Seems everything's back.
Okay, so I was here. Do you hear me? Can someone tell me if you hear me?
For me, it's perfect now. Yeah.
Yes.
I think it's okay. Sorry, but
now it seems you're on again, or am I having problems?
Yeah, I think you can hear me, but I cannot hear you. So I will continue with that. Sorry for the problem. So it was here with the horizontal elastic elements that are pinned at both sides. They enable shear transfer between one stud element and to another without influencing resistance. And these links, they represent, in fact, the concrete slab. And this modeling approach, it consists on a modification of the macro model described by Elgisser and others, where all the studs of a shear span are lumped at a unique location. And in this discretized model, the studs are discretized at their real location. So this modification, it allows accounting for a stud redistribution. So one stud can lose resistance and the other will distribute supplementary forces. And we will see a result about that later on during this presentation. Sorry, I don't know if you have the screen. Because
for me, it's still the screen with that you just talked about in the proposed modeling approach to simple composite sub-assembly description.
Slide 13.
Yeah, okay, now I think we've lost the screen. I mean, I can, or can someone else, if
okay,
you see, fine?
now
okay.
it's good, I think. Sorry, I have some issues.
No.
Okay, so then the beam spring, it follows an IMK deterioration model and with some modifications because it is now a composite beam. So I will not go in detail with this beam spring. The cyclic protocol of the conducted experiment is imposed to the model in order to compare the moment rotation behavior of the model with the one of the experiment. And at left, you can see a result for the lump model. So the initial macro modeling approach proposed by Elgisser and others, where all the studs of a shear span are lumped at a unique location. And at right, you can see results of the discretized model. So the modified macro model where shear stud elements are discretized at their real location. And these figures, they show that both model captures the experimental data in terms of moment rotation behavior. And it is therefore to highlight that the discretized model better represents the positive moment demand. Here are the force behavior of the stud. So the lump stud behavior of the lump model is in red, and it represents the effect of 22 studs of the beam. And concerning discretized stud, stud element 1 represents the stud located in the floor slab spring interval, and in our case, it represents 6 studs. Other stud elements, they represent the behavior of 2 studs because 2 rows of studs are disposed on the steel beam with this experiment. And we can notice that all the shear stud connectors remain elastic during the whole loading protocol for the lump and for the discretized model. And the slip demands, they vary between the different studs of the discretized model. So in this case, with positive bending, demands are less for the studs located near the column edge, and demands are more or less similar for other studs. And one reason to explain this tendency could be that the studs are more or less restrained by the concrete slab near the joint zone. So because the original subassembly was designed as a full composite, plasticity in studs can be observed when only 40% of the connectors of the experiment are disposed in the model. So when the studs experience plasticity, discretized shear studs deform less than the lumped shear stud. And in fact, when a discretized shear stud enters in plasticity, the other elastic studs will share additional forces if they can. And this is the redistribution principle. So the third and last model is a two-story, two-bay composite steel moment resisting frame subsystem, and it represents LG-SIR's experiment. So to remind, the bare structure of this experiment has been analyzed before with the bare subsystem model. And this last analyzed subsystem is created using the presented modeling approach, and I will therefore only focus on results. So here you can see a comparison of moment rotation behavior of the model with the experimental data at each joint location of the structure. It can be analyzed. So the model, it captures the general trends of the experimental data in terms of moment rotation relationship. And we can note the following three main points. The first one is that the model captures concrete crushing on the slab. So positive moment resistance is decreasing relatively quickly at small rotation. And this tendency is in fact related to the axial spring that represents the bearing of the slab mechanism, because after reaching capacity, this spring loses rapidly resistance. The second point is that the model underestimates negative moment resistance of interior west and exterior east joints at high rotation, because in fact, it does not account for the straightening buckling effect with cyclic loading. And the last remark I can make is that the cracks were developing in the steel beam at high rotation during the experiment. So this effect is not captured by the model, and moment resistance is therefore overestimated at high rotation. That's it. Okay, I will now use the presented modeling approach and analyze the seismic behavior of a real composite building. So the analyzed building is located in Sion, in Switzerland, and it contains 6 stories for a total height of 24 meters. So the building is formed of 4 composite steel moment resisting frames, so 4 MRFs in the east-west direction. There are 2 exterior MRFs and 2 interior MRFs as shown in the figure. And the building is formed of 2 concentrically braced frames, so 2 CBFs in the north-south direction. And the building was designed by LG-SIR in accordance with the Eurocode specification, and it is to highlight that the composite subsystem has been developed to represent this 6-story building, and that the conducted push-out test illustrates its composite slab. The model of the building is 2-dimensional, and it only accounts for MRF behavior, so the east-west direction from the previous slide. And by symmetry, one half of the structure is modeled, and one interior and one exterior composite steel MRF are constructed and placed into a series. And axially rigid elements that are pinned at both sides are disposed between the structure parts, and they enable them to work together. So the exterior MRF composite beam are differentiated to the interior MRF composite beams by accounting for a different effective concrete width. And the elements are following the modeling approach of the presented composite subsystem. So LG-SIR and other probabilistic seismic hazard analysis for Sion is considered here for our building location. So 2 distinct sets of 40 ground motions are selected to describe 2 earthquake intensity levels. So the first set, it represents the design basis earthquake, so the DBE intensity, and it corresponds to a regional period of 475 years. The second set, it represents the maximum considered earthquake, the MCE intensity, and it corresponds to a regional period of 2,475 years. And all these ground motions, they can be imposed at the base of the model to analyze the seismic behavior of the structure. Ground motion of each ground motion set are imposed to the structure, and slip demand of each shear connectors can be extracted from the numerical model. So these figures, they show a maximum slip demand per floor for the 2 different ground motion sets. and GBE results are presented at left, whereas MCE results are presented at right. And in these figures, each gray line, it represents a specific ground motion. So the black line represents the median of the 40 ground motion of the corresponding set. And we can observe that median maximum shifted slips do not overpass 1 millimeter for GBE intensity and 2 millimeters for MCE intensity. And we can also observe that shifted slips are higher at lower stories, and this can be explained because the flexural demand is higher at lower storage locations. So knowing maximum slip demand at 2 earthquake intensities, Jayer and Cornell methodology is used to draw maximum slip hazard curves for each floor location. So this methodology, it enables to determine a maximum slip value per floor for a continuous range of earthquake intensity. So in this figure, the x-axis, it shows the median of the shifted maximum slip, and the y-axis shows the annual frequency of the earthquake. So this frequency is in fact directly simply related to the earthquake intensity, as it is the inverse of the return period. And it is therefore possible to select the earthquake intensity we want to analyze and to get the corresponding shifted maximum slip value for a specific floor. And in the presented figure, the 3 horizontal gray lines, they correspond to 3 earthquake intensities, so intensities for return period of 72 years, 475 years, and 2,475 years. Now, Elgister and Lignos, they developed slip-based fragility function in order to evaluate the probability of exceeding a different damage state in the beam-slab connection, knowing the slip demand. So these probabilities are assumed to follow a log normal distribution, and their parameters were determined from various cyclic push-out tests from the literature. And 4 damage states are described in the paper. So there is DS1 that corresponds to light cracking in the concrete. DS2 corresponds to extending cracking in the concrete and stud yielding and concrete crushing near the base of the shear stud. DS3, that's extensive cracking in the concrete and low cycle fatigue micro cracking in the shear stud. And finally, DS4 corresponds to the loss of the shear load carrying capacity. And the presented figure here, it represents this slip-based fragility function. So now, using this fragility function together with the presented hazard curves, it enables to quantify the probability of exceeding damage states in the beam-slab connection for different earthquake intensities. So effectively, from the hazard curve, we can predict the exhibited slip of the earthquake intensity we want, and we can then link these slips to a specific damage state by using the probability function. So the figures at right, they give this information, and we can observe the following. So at service level earthquake, so for a return period of 42 years, the beam-slab connection only experiences probability to surpass DS1, and this damage state has a probability of about 40% to be reached, and is acceptable in the design as it only affects the cosmetics. The second remark I can make is that at design basis earthquake, so for a return period of 475 years, the beam-slab connection has a high probability to reach DS1, and it has a probability of less than 1% to exceed DS2, which is acceptable damage state in seismic design. And at maximum considered earthquake intensity, so for a return period of 2,475 years, overtaking DS2 has a probability of less than 16%. And for the seismic intensity, the probability for the connection to experience extensive cracking in the concrete slab or low cycle micro cracking in the shear stud, so damage state 3, is less than 2%. And after all, reaching a damage state associated with the loss of the shear load carrying capacity, which corresponds to the S4, is negligible for all the analyzed earthquake intensity. So conclusion, this presented headed shifted analysis from composite building simulation, it shows that the beam-slab connection is only slightly damaged when it is subjected to a design basis earthquake. So at this intensity, shifted connectors, they experience slip demands that do not overpass 1 millimeter. And with cyclic push-out test, shear stat behavior is completely different because the connectors are loaded by incrementally increasing completely reverse slip demand cycles until the rupture. And these loading protocols are severe and they lead to brittle damage state. So these results, they suggest that the 25% reduction factor related to seismic strength of headed shear stud connectors is not imperative to maintain the integrity of the composite connection in the case of the analyzed composite slab geometry. And it therefore seems reasonable to waive this aforementioned requirement for beams with depth less than 500 millimeters. And finally, as an extension of this work, the effect of different composite slab types on the damage state probabilities could be investigated. And several steel beam depths, profile steel sheeting geometries, and concrete slab over thickness could be studied in order to be able to generalize the findings of this work. So here are some references of this work. And thank you very much for your attention, and sorry for the issues I had during the presentation. I hope it was okay for you.
Oh yeah, thank you very much for this very interesting presentation. And yeah, no worries with the issues. I think that's nowadays coffee, small talk chat, the technical issues. No, so do we have any questions? Think there is nothing in the chat yet. So if you want to, you can raise your hand. Maybe either write them in the chat or raise your hand and ask questions directly. Maybe I'll start us off with one then. I think you kind of answered it with the last slide already. I had the impression, like with the modeling results that you showed, it seemed that for the 475-year earthquake for this building that you studied, at least the studs remained in damage state 1. So it's, I don't know if we can say more or less elastic. So so do you think that maybe like a standard design for the according to the SEA would have covered the forces in the stud, or like would have been good enough without? I mean, you mentioned this 25% requirement could be waived, but I wasn't sure. I think the SEA was a little less conservative than the Eurocode and the other codes that you mentioned.
Yes, in SIA there is nothing written about that, and this 25% is only written in the European standards or Eurocode and the American standards, AIS.
And then maybe one question to related to the modeling. So in this case study that you had, did you have a reversal of the loads, like of the moments in the corners? Like, was it really a reverse cyclic loading on the studs, or?
Yes, so it was reversing, so in the other direction, but most of the loading was in one direction. So it's why it was going in the positive direction.
Okay. Oh. Okay, thanks. So, I don't know, it seems no more questions on the chat. No one, or do I miss someone raising the hand? Everyone's hungry, or or you answered all the questions in the presentation, apparently. Yeah, if it seems like people are leaving, then I think yeah, there are no more questions. Thank you very much for this very interesting
sorry
presentation.
one more time for the problems I had. I hope it was okay.
No problem. No problem at all. Now we have Tadeusz.
Well, I don't want you to go. So I have one question just to understand the system you are calculating this model. In the middle of the beam, you don't have a connection. And I was asking myself, well, what is the reason?
Yes.
Could you explain this?
Yes. So in the middle of the beam, I assumed that there was no connection. So is it this? So the middle of the beam here, where shifted connectors are not linked at the right side and the left side. That's what you said, right?
Yeah.
Okay.
Yeah.
Yeah. So I just assumed that it was completely acting separately, and it was an hypothesis for this model, because first I tried to make a link between it, and the results were just not nonsense. So it's why we separate the both sides of the beam.
Okay, because from the let's say engineering point of view, this connection has influence on the stiffness of the beam. It's not for dead load is you have the compression there. So it's not very intuitive that you can omit this connection, but. I have to sleep on it.
Okay.
Thank you very much.
Thank you.
Any more questions? Well, if not, then I say thank you very much. It was really interesting.
Thank you.
Presentation. Thanks a lot for accepting to present that. And have a nice day, everyone, and bon appetit for those that are going to lunch now.
Thank you very much.
Thank you very much.
Bye.
Was excellent presentation. Thank you.
Yeah. Thank you very much. Bye-bye. Bye.